Hello dear GATE aspirants, welcome to VEDA GATE Academy. Today we are going to start with the subject control systems. One of the very important subject for any technical examination, that may be GATE or ESC or ISRO exam or any other exam. Control systems is very important, not only for examination. The industry, with respect to industry also, control systems is the very important module to learn. Okay, so let's get start with our subject. First, let's discuss the syllabus. Means what are the topics we are going to cover in a sequence. Sequence is very important. It's not that first topic can be dealt in the last or last topic can be dealt in the first. We have a very good sequence. That sequence has to be followed. First, let's see the syllabus, then we enter into the topic. First topic, come on, look at the syllabus please. The first topic of our control systems is basics of control systems. Yes, the name itself. For studying entire control systems, what are all the basics required? We are going to study in this first chapter. If you are not in a position to understand anything in the first chapter, it's very important to ask the faculty that particular thing what you didn't understood. Why? Because this will serve as the basic for entire control systems. Please understand everything in this and do not miss any class in the first chapter. If you miss any class in the first chapter, definitely you are not going to understand anything in the remaining control system chapters, please. So this will serve as the basic fundamental. Yes, that is a fundamental topic for the entire control systems. What we will discuss in basics of control systems, let me tell you. Yeah, you know very well, control systems is discussed in S domain. Entire control systems is discussed in S domain. Those who are done with the control systems in BTech, you might be knowing at least something. Entire control systems is discussed in S domain. What is the reason for that, sir? We will discuss it later in the chapter. Yes, when we start this chapter, we are going to discuss. We have two domains. One is time domain, another one is frequency domain. What are the advantages of frequency domain? We are going to see. What are the advantages of frequency domain? We are going to see. How to convert from time domain to frequency domain. Again from frequency domain to time domain. What is the tool we are going to use to convert from time domain to frequency domain to time domain. Everything we are going to see in this first chapter, please. Not only that, in control system, one of the very important thing is transfer function. Those who are done with control systems, they might be aware of it. Transfer function. Those who are not done with control systems in BTech also, please concentrate well. We are going to start from the scratch, please. Okay, very basic onwards we are going to start. So transfer function, poles, zeros, what not, everything, all the basics required for this entire control systems we will be discussing in first chapter. Not only that, in the first chapter we are going to represent our electrical circuits like RC, RL, series RC, parallel RC, series RLC, parallel RLC, all these things in S domain. What are the advantages of S domain in electrical circuits also we will discuss in first chapter. Once we are done with the first chapter, we will enter into the second chapter. Come on brother, what is that second chapter? Block diagrams and signal flow graphs. See, practically we have very big systems. System is very big, which is having a lot of subsystems. All those will be represented very easily with the help of signal flow graphs and block diagrams. We have two things here, signal flow graph and block diagram. You may get a doubt, sir, we have signal flow graph, then why you are going for block diagram? Or we have block diagram, why we are going for signal flow graph? All those things, advantages, disadvantages, all those things we will be discussing in second chapter. Third chapter is time response analysis. One of the very big chapter and one of the very important chapter with respect to GATE examination is third chapter. First two chapters more or less will serve as a basic. Okay, third chapter here really our analysis will start, time response analysis. In time response analysis, we are going to study about actually we will study in a mathematical way, but indirectly we are studying about RC, RL, RLC, series RLC, parallel RLC, those circuits indirectly, not directly. Sometimes directly we'll study by taking examples. With respect to time, how the response is changing. See, if you take a system, to that system we will give some input, then we will study about the output. That output or response will either increase or decrease. Definitely it will change with respect to time, except for DC case, DC and purely resistive network. If the input is DC, the circuit is purely resistive, output is constant with respect to time, it is not going to change. But here we are studying about mostly about first order onwards. Order zero means what? We'll see what is order. We'll see what is order also in in the first chapter itself, we are going to see what is the order. Okay, so in third chapter, we are going to study about mostly first and second order systems. I'll give you a small hint what is order. If you take a purely resistive network, what is purely resistive network, sir? Which is containing only resistances R1, R2, R3. That is called as order 0 circuit, order 0 circuit or order 0 system. Then what is first order system? The system which is having at least one energy storage element, or first order circuit means at least one energy storage element. Series RC, parallel RC, yes, series RL or parallel RL. These are first order systems. Second order, order stands for number of independent energy storage elements. What does it mean by independent? That also we are going to see in the first chapter, please. Okay. Second order means series RLC. We have two independent energy storage elements, L and C. Parallel RLC. Yes, second order circuit. Those second order circuit responses for different inputs. Yes, time domain specifications like rise time, delay time, peak time, settling time, percentage peak overshoot, whatnot. Many things we are going to see in third chapter. And one more important thing in third chapter is steady state error. There is a possibility to get some error if we design a system for a particular input. How much is that error? How to calculate? How to reduce that error? What are the reasons for that error? All those things we'll be discussing in third chapter. Okay. Fourth chapter is very important. From fourth chapter onwards, yes, we are really entering into the control system, what you call stability, control system stability. Yes, what does it mean by stability? What exactly stability means we will be studying here. Physical analysis. We always do physical analysis, not mathematical analysis. First, we will do physical analysis, then we take the help of mathematics. Then our physical analysis is going to be much beautiful. Okay, so for everything, for every point, I am going to give you a reason. Yes, for every point, I will give you a reason. Without reason, we are not going to learn anything, please. Here, stability. We actually, those who are done with control system, they might be knowing RH criteria, Routh-Hurwitz criteria is used for the study of stability. Here, we are going to see the very basic onwards of what does it mean by stable system. What does it mean by stable system, unstable system, marginally stable system? Why poles are only used in the study of stability? All those things in a very clear manner we will be studying in stability. A lot of shortcuts we are going to learn in stability. Means if a fourth order characteristic equation is given without using pen paper, if you are good at oral calculations, just by looking at what you call the characteristic equation, we must be in a position to tell whether the system is stable or unstable. For some examples, not for all examples, because there are some limitations for the shortcuts. Okay, so that is stability. Now, this stability by using RH criteria is having some disadvantages. Yes, a lot of disadvantages are there. See, along with advantages, disadvantages are also there. To overcome those disadvantages, one new chapter is introduced. So the next topic is root locus diagram. In fact, we are using Evan's method. Evan is a scientist. Yes, Evan is a scientist who given some method to sketch a root locus. By using that method, we are sketching the root locus. In root locus, we have total 4 modules. That is root locus of a negative feedback system. So by default, if nothing has been mentioned, root locus means it belongs to negative feedback system. Root locus of a positive feedback system, this is the second module. Inverse root locus of a negative feedback system is the third module. Inverse root locus of a positive feedback system is the fourth module. So we will learn how to sketch root locus very easily, and for some difficult questions, how to find stability by using root locus also we'll see. In this chapter, we are going to find the stability of some difficult what you call problems. Not only that, some time response specifications also we are going to find in root locus. After completion of root locus, we will enter into the topic controllers. Yes, controllers. Yeah, here I want to mention one point, that is this controllers is not there in syllabus for gate examination, but anyhow I will be discussing. That is useful for the examinations like ISRO and HBCL, some other exams, some other technical exams, whatever may be the technical exam. There is a possibility to get a question from controllers. For ESC, engineering service examination, that is IES, controllers is very important. So by keeping that in mind, I am discussing controllers. And one more thing, if you go for an interview for IITs or to some PSUs, if you go, they may ask some questions from controllers. See, please keep in mind that the interviewer, if you go for ISO or DRDO interview, the interviewer will not ask a question from the gate syllabus, please, from the gate syllabus itself. So by keeping all these things in mind, I will be discussing control systems also in depth. Okay, but do remember one thing: no direct question will be given from controllers. Indirectly, see, sometimes in the question the examiner will mention as a controller, but without knowing the concept of controller also, that question can be discussed or that question can be solved. Okay, please keep this in mind. The next topic is introduction to frequency response. Yeah, I want to mention one thing here. Up to controllers, our analysis is time response analysis or time domain analysis. Time domain analysis means everything we speak with respect to time increasing, decreasing, or constant. These things with respect to time we will discuss. But once we enter into the 7th chapter, that is introduction to frequency response, means here completely with respect to frequency, here we are changing frequency from 0 to infinity, please. Omega from 0 to infinity will change. Angular frequency, omega means, omega is what? Angular frequency. Introduction to frequency response means in this chapter we are going to see gain margin, phase margin, okay, resonant peak, okay, these things we are going to see. How to find stability by using frequency response also we are going to see, by using gain margin and phase margin for minimum phase systems or non-minimum phase systems, whatnot, lot many things we are going to discuss. So with respect to me, up to 6th chapter, it is one what you called one half. That is, I'll call it as first half. From 7th chapter onwards, it is going to be called as a second half. Okay, means the techniques up to 6th chapter are of one way. Okay, from 7th chapter onwards, the techniques are going to be completely different. So introduction to frequency response, there we are going to learn a lot of basics. How we learned basics in the first chapter with respect to time response. Here in 7th chapter we are going to learn the basics of frequency response, like gain margin, phase margin, resonant peak, resonant frequency, bandwidth. These things we are going to learn, and finding stability by using this frequency response. We have some disadvantages. Finding stability by using gain margin, phase margin with the formula directly, means gain margin formula we have and phase margin formula we have. By using those formula, if I want to find stability, it will be difficult for some questions above 3rd order or 4th order. So that also we'll see what are the disadvantages. Then we go for Bode plot. We sketch Bode plots. Bode is going to have 2 plots, that is magnitude plot and phase plots. Two plots can be drawn separately, not on a single what you call a paper. 2 different plots. Those are phase plot and what you call magnitude plot. With the same reference we can draw. With the same reference, frequency reference we can draw. Bode plots, very important, please. See, in Bode plots, just by looking at the Bode plot, we must be in a position to write the transfer function. See, actually, in the first module, we will learn how to draw Bode plot for the given transfer function. But in GATE examination, nobody is going to provide a pen and paper to you to sketch Bode plot. Most of the questions are, the examiner will give a Bode plot to you. He will be asking you what is the transfer function belonging to that Bode plot. Obtaining the transfer function from the given Bode plot is going to be called as inverse Bode plot. Okay, see, we are not going to sketch any plot, but we are in a position to find the transfer function from the given Bode plot. That is Bode plots. Bode plots. After that, we are going for polar plots. After polar plots, in polar plots, by using polar plot also, we are going to learn how to find the stability. After completion of polar plots, we will be entering into Nyquist plots. So Nyquist plot is very, very, very important. Every year in GATE examination, definitely one question based on Nyquist stability criteria. Definitely, that is damn sure. Okay, so extension of a polar plots is a Nyquist plot. If we are able to draw polar plot, then with some extension we'll be in a position to draw Nyquist plots. With the Nyquist plots, we are done with the plots part. Then the next chapter is compensators. Yes, this compensators is there in syllabus. We have lead compensator, lag lead, and lead lag. 4 are there in syllabus. We will be learning compensators. We are going to sketch Bode, polar, Nyquist plots for the compensators. What we learned. Okay. See, we learned previously Bode plot, polar plot, Nyquist plot. For those plots, we are going to draw for this lag lead and lead lag compensators. So with this up to 11th chapter, from 7 onwards 11, we are done with frequency response also. Okay, from 1 to 6 it is time response or time domain analysis. 7 to 11 it will be frequency response analysis. Now 12th chapter is the modern control system, we call. This is very important. If you go for MTech in control engineering, please. Yes, MTech in control engineering, then definitely this is going to be the first chapter you are going to learn in MTech control systems. What is that? That is state space analysis or state variable analysis. State variable analysis. Okay, modern control systems we call, or modern control theory we will call this. This is also very, very important with respect to GATE examination. Every year 1 2-mark question is guaranteed from that 12th chapter, that is state variable analysis. Up to 12th chapter, we are done with the syllabus of ECE. Electronics and Communication Engineering student syllabus is done up to 12th chapter. Now 13th chapter is there only for EE, please. I am writing here, this is only for EE, electrical students, please understand. Only EE students will follow this. Up to here EC syllabus is done. EE students are also having extra one chapter, that is a 13th chapter, that is mathematical modeling. There we are going to find how to model mathematically. In fact, we can teach this one in the first chapter itself, but as that is not there in GATE syllabus for EC students, we will be discussing this one in the last chapter. So this is our syllabus, just the intro, means what are the topics we are discussing, what we are what you call studying in those chapters briefly, just I given, not completely. Once I enter into the topic, there we will be discussing what are all the topics we are discussing step by step. And my teaching methodology will be like this. Please follow this. What does it mean by that? Means I will teach first the technique, then after that I will be discussing where it is applied. Please do understand. First we will learn the technique, then we will apply later in the application. But some people, they will list out all the applications in the first, where root locus is used, all they will list out in starting itself. What I feel is that is confusing. But because if you don't know what is technique, if I tell you the application also, there is no connection in your mind. Okay, in this place this has to be applied like this. You won't be getting any connection. That's why first let us learn the technique. In the last we'll see the applications, advantages, disadvantages. To overcome the disadvantages, what to do. Okay, this is our methodology. First, all techniques, procedures we will learn. Okay, I am not going to give all the applications in the first in the starting itself. Okay, and after this, references, textbook references. See, one point I want to clarify here. Please do not read any textbook in the starting. Yes, do not read any textbook in the starting. If I complete basics, then you read basics from your textbook. In that also, what the doubt you get or what is the extension you want, that particular thing only you read from textbook. Yes, you should not, or it is not required to read the entire line to line, page to page of any textbook. Not required for GATE examination, not only for GATE examination, for any other examination. Why? Because we will be giving all sufficient inputs here. If you get any doubt, clarify with the faculty. If not, you can refer a textbook. That is a good thing. Or if you want more examples to solve, we will be providing number of examples, or you can take from textbook. Or if you want to read about more number of applications, then you go for a textbook. Otherwise, please do not read any textbook. But the references, yes, you have to take these books, international books. This fourth one is a national author, but it is a very good book with respect to problems to solve. Okay, my point here is, whenever if you want an example, go for a textbook. Whenever you want an application, go for a textbook. But do not read the entire theory what is given in the textbook. We are here to give all that what is there in the books and what is not there in the books also here. So please follow the class carefully. That is sufficient. Do not waste your valuable time in reading all the points that are given in the textbook. Anyhow, we are very simply, in a short way, we are giving all those. Okay, the first book is B.C. Koo, Benjamin C. Koo, a very good book, international author. In a very beautiful manner, the book has been written. But to understand this B.C. Koo, a student must have some good basics from mathematics and signals and systems. So why we need the basics of signals and systems? Yes, I'll be discussing in first chapter. Wait for a few moments, we'll be entering into that. Okay, second book is Vogata. This is also a very good book. A lot of examples, but very in-depth examples are covered in these two books, please. In these two books. This third book is student friendly. I recommend third book, Norman S. Nice, if you want to read on your own few topics at least. Sir, I have the habit of reading a book. I want to learn few things on my own. I want to follow a book. Please, I'll recommend you this Norman S. Nice. Sir, I want to solve more number of problems. then you go for Anand Kumar. So these 4 books are enough if you really want to follow. Yes, this is the syllabus. And I forgot to give you the weightage of control systems in what you call gate examination. In gate, definitely every year, either it is a ECE or EE or instrumentation engineering, the number of marks we are going to get is some 8 to 12 marks. 8 to 12 marks we will be getting in this exam. Gate exam. In other exams, the weightage of control systems is more or equal to networks or any other subject, please. Okay, it is one of the major what you call the subject with respect to competitive examinations, technical competitive examinations. So we are going to learn in a beautiful way. Means we will be doing like a construction. See, one layer after another layer, one layer after another layer. In that way, we are going to learn. If you are missing the first layer of our control systems, second layer cannot be laid there. Please, it is not possible to lay second layer there. So it is very important from the first point onwards, not the topic, please. First point onwards. So I will be giving a connection from one point to another point. The point what I given to you in the first chapter, I am going to use in the last chapter. Okay. So in that way, our classes will be. So it's very important to listen to our classes fully, okay, with full concentration, without missing any point. You must listen. Then only you are able to understand. Otherwise, you will miss the connection. Yes, you have lots of dots. If there is connection between the dots, you will get a figure, a beautiful figure. If there is no connection between the dots, you are missing the figure. You have lots of dots. That's it. Okay. So please carefully follow our class. So this is about syllabus and the textbook references. Every day, I will be providing 10 questions on the topic what that we have discussed in the class. So that is called as CRQ, concept revision questions. Yeah. To revise the concepts what we discussed in class, I will be giving 10 problems in a day or more than that. It is my recommendation to solve all those 10 problems on the day itself. I will be providing you the key. Compare your key with my key. Then if there are any discrepancy, directly you can call me. My number is provided to you. Yes, all faculties numbers are provided to you from VEDA Gate Academy. Okay, solve CRQ. After solving CRQ, we will upload. Yeah, I think it has been already uploaded control systems material to you in your what we called app. In the app, VEDA Gate Academy app, control system material is present. Okay, please start solving questions from previous. First, you solve previous gate questions, please. Previous gate questions. We provided past 26 or 28 years gate questions. All 3 branches, EC, Trivia and Instrumentation. So more or less some 600 plus questions will be present in that material. VEDA previous gate material for control systems. Okay, VEDA previous gate material for control systems is present in your app, VEDA Gate Academy app. Try to solve those questions. After that, you go for practice gate material. 400 questions are provided exclusively from control systems for practice. So that is called as practice gate material. After this, you can write examinations that we are providing in VEDA Gate Academy test series app. So with this, your preparation will be completed. So this is the procedure. First, listen to the class carefully. Solve all the problems given in class. After that, CRQ, concept revision questions are provided to you every day. 10 questions. Solve those questions. After that, material questions that are present in VEDA Gate Academy app. After that, practice previous gate questions, practice gate questions. After that, test series. So this is the procedure what you have to follow. If you get any doubt at any point of your preparation, all our faculties are available. So please just call or SMS our faculty. Our faculty will help you in all directions required to you. So let's get into the topic. That is, first topic is basics of control systems. The first topic is what, ma? Basics of control systems. Yeah. So first point what I'm going to discuss here is entire control systems is discussed in S domain. Means calculation is done in S domain. You might be thinking, sir, what is S domain? Frequency domain. Sir, what is S? S is a variable. S is a variable or operator. I call Laplace operator is a S. What is S, sir? S is equal to sigma plus j omega. S is equal to sigma plus j omega. Sir, what is this sigma? What is this omega? What is this j? All these things we will discuss. Yes, sir. Slowly we will enter into that. First, let's understand why control systems is discussed in S domain. Calculation is easy in S domain. Yeah. Let me write the first point. See, for every point what I am discussing now, the proof will be given now or later. If I am giving the proof later, I will be definitely telling here that we will discuss the proof later, or the example for this statement will be given later. Definitely at that point of time I will be giving. Come on here. Entire control systems. See, this is not in syllabus, please. Basics of control systems means not belongs to syllabus, but to understand and execute the topics what are there in syllabus, this topic is very, very important for us. That's why you all must listen very carefully here. Entire control systems is discussed. Control systems is discussed in S domain. Discussed in S domain, please. Yes, entire control systems is in what domain? S domain. We have two domains. How many domains we have? We have two domains. We have two domains. Two domains. Okay. Please write notes. We have two domains. One is time domain, another one is a frequency domain. The first one is time domain. Time domain. Yes. Second one is frequency domain. Frequency domain. Sir, why we are going for frequency domain? Actually, we have time domain that everyone knows. Yes, everyone knows we have time domain. Sir, how do we know we have time domain? Everything will speak with respect to time. Suppose you are coming to the class. Today you are coming or not. Tomorrow you are coming or not. Yesterday you came or not. Means everything will discuss with respect to time. Okay. That total this world is running with respect to time. This one everyone knows time domain. Sir, we have time domain, then why we are going for a frequency domain? I'll tell you simply a point. You are sitting in the first bench in your classroom, but you are changing your bench from first to last or third or fourth. Why? There is some problem in the first bench, or there is some discomfort for you in the first bench. That's why you are going from first bench to second or third or fourth or last. Fine. This is a small example. This is a small example. Now, what I want to convey you exactly is there are some difficulties in time domain. Yes, there are some difficulties in time domain. Immediately a question might rise in your mind. Sir, what are those difficulties? Yes, I will discuss. I will list out all the difficulties in time domain, how those are going to be overcome in frequency domain. I will be discussing. Definitely I will be discussing. Please do remember these 2 points first now. For time being, you will remember in the upcoming classes with the proofs. Why? Because now, even though if I give a statement, calculation is going to be easy in frequency domain, if I say, you won't be in a position to believe. Why? I'm not giving any example. If I want to give you some examples, we have some basics to cover yet. Therefore, please do remember one point. There are some advantages in frequency domain. That's why we are going for frequency domain, from time domain to frequency domain. What are those advantages we will be covering later, yes, in the upcoming classes. Okay, that's why we are going from time domain to frequency domain. Now tell me one point, what is a human understandable domain? Come on dear, human understandable domain is always time domain. Yes, if you tell me with respect to time something, see, that person is running with 20 km per hour. I am in a position to understand. If you convert that 20 km per hour into some frequency, something, blah, 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 if you tell me, I am unable to understand. Human understandable domain is time domain. Practical domain is time domain. But we are going from time domain to frequency domain only for the purpose of calculation. After completion of calculation in frequency domain, again we will convert from frequency domain to time domain. Frequency domain to time domain. Okay, please do remember these points. Then let's go for how to convert from time domain to frequency domain or frequency domain to time domain. We have some tools to convert from time domain to frequency domain or frequency domain to time domain. What are the tools? That is Laplace transformation and Fourier transformation. We have some tools to convert a given signal or a function from time domain to frequency domain and frequency domain time domain. Those are what what you call Fourier transformation and Laplace transformation. Fourier is having some limitations. That's why we are going for Laplace transformation. What are the limitations of Fourier transformation when compared to Laplace? You will be learning in signals and systems. That is not our cup of tea here to discuss. Why? Because there are so many things to learn in signals and systems. These 2 points what I am discussing belongs to what you call signals and systems. So definitely those points will be covered in signals and systems. But one point here is we are taking the help of Laplace, not the Fourier. So the point here I'm writing here is Laplace transform is the tool. Laplace transform, yes, come on dears, transform is the tool that is used to convert from, come on ma, from time domain to yes, frequency domain, yes, frequency domain. Simply I'll be writing that one in mathematics. That is if we have a function f of t, yes, f of t is in German ma, yeah, very simply you can tell that is t, time domain. Then how to convert into frequency domain? Apply Laplace transform. You are going to get f of s. So one thing we must be clear, that is terminology and notations. F must be capital. In time domain it is small. In frequency domain it must be capital. And s is also t. Here t it is small. Here s must be capital. Here f of s. F of t is in time domain. F of s is in frequency domain. Then how to convert from frequency domain to time domain? Inverse Laplace transform. Yes, we have f of s. Then apply inverse Laplace transform. Then you are going to get f of t. Laplace transform and inverse Laplace transform. So we must be very clear in Laplace and inverse Laplace transforms. Why? Because the entire control systems is discussed in S domain. All of you must be very good at Laplace and inverse Laplace. We are going to discuss about Laplace and inverse Laplace transforms or to our required extent. Means I'm not going to discuss everything like ROC and all those things. Those things we will discuss in your signals and systems. What are the basics of Laplace transforms and inverse Laplace transforms required for me in control systems? I will be discussing. Okay. So how to convert a signal or a function in time domain to frequency domain by using Laplace transform. Then what is the formula for converting? Yes, what is the formula for converting? Yes, if f of t is a signal, yes, come on, signal in time domain, come on dear, in time domain, then f of s is equal to, come on, I think most of you know this. Why? Because in first year, in your BTech first year, you might learn mathematics. In mathematics, yes, it is present, converting from time domain to frequency domain to time domain, Laplace and inverse Laplace. Then f of s is equal to integral minus infinity to infinity. Yes, integral minus infinity to infinity. See, understanding this one is very important. How to apply? Which signal you want to convert? Yes, sir, I want to convert the signal f of t. What are the limits of integration? Minus infinity to plus infinity. Yes, we will take minus infinity to plus infinity. But if the signal itself is existing from 0 to infinity, then automatically integration limits will change from 0 to infinity. See, we will take from minus infinity to plus infinity. But actually, what are the limits that are going to be taken in the calculation will be decided by the existence of f of t. Into there is an operator. This is called as a kernel. Yes, kernel, which is used to convert from time domain to frequency domain dt. Yes, see, very simple. Take the function what you want to convert from time domain to frequency domain, multiply with a kernel e power minus st. Okay, then you integrate that product from minus infinity to plus infinity. Then you are going to get f of s, where s is Laplace operator, or It is also called as a complex frequency. Yes, it is also called as what ma? Complex frequency. Complex frequency. The proof for everything we will be discussing by taking examples in the upcoming sessions. Please hold all your questions or all your what you call doubts. Yes, until upcoming sessions where S is equal to sigma plus j omega. Sigma plus j omega. Sigma is called as Nepper frequency. Nepper frequency. Yes, Nepper frequency in Neppers per second. In Neppers per second. Sigma is called as S is complex frequency, summation of two things. This omega is frequency, then sigma also must be a frequency. Many people don't know sigma as frequency. They will call it as a real part. They will call this one as imaginary part. Yes, even an intermediate student is able to tell you that this is the real part, that is imaginary part. That is not important, please, brother. Here, the important thing here is sigma is called as Nepper frequency. That is also a frequency. Okay, what is the significance of that? We will be seeing later. Omega is called as what? Omega is called as angular frequency. What ma? Angular frequency. Yes, whose units are radians per second. Whose units are what ma? Radians per second. Omega is called as what? Angular frequency. S is the complex frequency, sigma is the Nepper frequency, omega is the angular frequency. What is the significance of sigma? What is the significance of omega? All these things, by taking some very good examples, I will be proving. Okay, why we take an S is equal to sigma plus j omega. What is the significance of sigma also I will be discussing. Please wait till that time, then you will get complete clarity. Just this is an introduction, please. Introduction only. Please do remember that point. Yes. Now, how to convert how to get inverse Laplace transform? We are not required, means we did not require any formula for finding inverse Laplace transform. If we know Laplace transform, definitely we are going to get inverse Laplace transform without using any formula, just with a direct inspection methods. We are going to see those direct inspection methods also. So let me list out all the points here what we discussed till now. Entire control systems is discussed in S domain, that is frequency domain, where S is equal to sigma plus j omega. Sigma is called as Nepper frequency, Nepper per second. Omega is called as angular frequency, radians per second. The tool that is used to convert from time domain to frequency domain is a Laplace transform. And the tool that is used to convert from frequency domain to time domain is what ma? Inverse Laplace transform. How to convert into S domain? That's the function what you want to convert. Take suppose it is f of t, integral of minus infinity to plus infinity f of t, e power minus st dt will give f of s, where e power minus st is called as what? Kernel. Okay, is called as kernel. Now come on here. After this, one point I want to discuss here, one very important point. Imagine we have a system. System means I will be giving the definition of system, control system, time invariant control system, time variant control systems, linear, non-linear, whatnot. All these things I will discuss more. Just imagine a system. Then you may get a doubt, sir, what is a system? Let me define a system, or let me give you a statement regarding a system. I'll tell you very simply. First, let me take an example of a system, then I'll define. See, the fan that is rotating in your classroom is a system or not? Yes, obviously it is a system. Now let's define the system. It is an interconnection of, what is system? System is an interconnection of components or elements, okay, to do some desired task. Yes, let me complete it again. Yes, system is an interconnection of, yes, you are taking some elements, some components. Fan is going to have wings, and inside there is a motor, and that there is a winding, and there is some capacitor. Electrical students might be knowing what motor is used in fan, all these things. Yeah, it is a system. We take in some components, we interconnected. Why we interconnected? To perform a desired task. What is the task that fan is doing? The task that is performed by the fan is producing air. Fan is a system. Yes or not? So let us take a system. See, here taking a system means we are not taking physical system. We are taking the mathematical model of the system. See, any system you take, in control systems, what we are doing is, whatever may be the system that is available practically, we will take that system, mathematical equation of that system we will get, we will operate on that mathematical equation, Yes, if we are operating on that mathematical equation, means we are really operating on the system, the practical system. And if the output that mathematically changes, practically the same thing is going to happen. That is what we are going to do here. Mathematically we are doing here before we design a practical system. If mathematically, if it gives correct results, then only we go for practical design. So simply, more or less, we are doing simulation, but not by using computer. Mathematically, we are doing on paper. Okay, come on here. I'm taking a system here. Here we are entering into the topics slowly. Yes, I'm taking a system here. Yes, I'm taking a system. Means we have the mathematical equation of that. Yes, suppose fan is a motor equation we taken, we just kept here. Okay, now I want to know whether this system is working properly or not. What to do, brother? Come on, brother, you can answer. How to check whether this system is working properly or not? What does it mean by working properly? I have some desire for this system, means I want this system to work in some direction. Okay, suppose if it is a fan, I want this system to rotate with 100 rpm, 100 rotations per minute, 100 rpm. Now I want to know whether this is working properly or not. See, a motor is going to have rpm, torque, many things, but for just for the sake of example I am giving here, I want to know whether this is working properly or not. What to do, brother? Give some input, check the output. Yes, excite the system with some input, get an output. If the output that is obtained here is according to your requirements, then you can directly conclude that this system is working properly. If not, where the problem is, how to solve that problem is. This is our duty being an engineer. Yes or not? Yes. Remember one point, brother, we are at the very basic. Lot of examples, lot of applications, lot of techniques we have to discuss. We are at the very starting. Okay, so the clarification, some points you will be obtaining in the upcoming sessions. Okay, please do not try to get the total clarification here itself. You will get confused. I am promising you all the points what I told we will discuss later. Definitely I will be discussing later. Okay, we are giving some input here and we are checking for the output. If the output is according to my requirement, I can say that my system is working properly. Otherwise, we have to solve the problem. Means where the problem is there. First of all, we have to find the problem, reason for the problem, then solve it. That's it. Means we have to give input and check the output. Here we are doing practically or mathematically. Mathematically. In laboratory, first of all, we have to do mathematically. First of all, the mathematical model that is designed by you must get approval. See, if you go for MTech or PhD, if you are designing some if you want to design some practical model, first of all, that practical model must get approval mathematically. Means in this way, prototype, first of all, you have to design. That one you have to simulate by using computer or like this manually by giving some input and output. After studying the results, then you will get the approval for designing a practical type. So that's what we are doing in control systems. Here we are giving input and we are getting some output. Input is nothing but a signal. Yes, input signal. Yes, output is also a signal. Output is also a signal. How to check my system whether it is working properly or not? Give some input signal, get the output signal. You see the output signal whether that is according to your requirement or not. Then we can say whether it is working properly or not. Means what? We must have good basics on signals. See here. I will give some exponential signal as input to this one. If you don't know mathematically how to represent an exponential signal, then you will fail definitely. Because if you don't know how to represent a mathematical signal, an exponential signal mathematically, you will commit a mistake. Definitely, it's not the system mistake. If you are not having strong basics on signals, you don't know how to write. Here, you write a wrong signal here. System is very good, but the output what you are going to get is wrong. Why? Because you did a mistake here in taking the input. It's not the system mistake. Then what you conclude? System is not working properly. No. System is working properly, but it's your innocence or it's your lack of knowledge in representing a given input signal. That's why you got a wrong answer. So we all must have good basics on signals. Okay, sir. Sir, does it mean you are going to teach signals and systems? No, boss. No, we are not going to take that risk because we have other faculty for signals and systems. And signals and systems syllabus is entirely different from control system syllabus. Okay, that syllabus is different. This syllabus is different. But what I'm going to do is I'm going to teach you all the signals what that are required for me in control systems. You got the point, ma? I'm going to teach the signals basics what that are required for me to understand control systems. Okay, let's proceed. Our next topic is basics of signals. Basics of signals. Come on, ma. Basics of signals. Yeah, in basics of control systems, the first topic what that we are going to discuss is basics of signals. Come on. First subtopic, please. Need not to give the numbering, please. Need not to give the numbering. Just it's an heading, subheading. Okay. Basics of, come on, signals. Basics of signals. Okay. Yeah. Those who are done with signals in your graduation BTech, you might be knowing the basic signals are. Yeah, come on. What are the basic signals, ma? Come on, dear. You can answer. The basic signals are impulse, step, ramp, parabolic, sinusoidal, exponential, saw function, sinc function, blah blah, many things. Tri-T, rect-T. Easy people might be knowing this. Triangular function, rectangular function. These things you know. But we have very limited usage of signals. Means all these signals are not required for us. We require impulse, step, ramp, parabolic, sinusoidal, and exponential. These 6 signals are important for us for control systems. If you are good at these 6, then it's a mathematical representation converting from time domain to frequency domain, frequency domain to time domain. This is enough for us with respect to control systems. The first and foremost signal we are going to discuss is impulse signal. See, brother, if you go to any interview, definitely a question will be asked from impulse signal. Yes, definitely one question will be asked because that much importance it got, impulse function. So you will be learning in signals and systems also what is the importance of impulse function. Okay, any function can be represented in terms of impulses that we will be learning in signals and systems. That is not our cup of tea. Your signals will take care of it. But how we want impulse function, we are going to discuss. Electrical students, those who did not study about signals and systems in BTech, don't worry. At least you might saw these functions in maths. Yes, signal. See, impulse. You might study it as Dirac delta function, impulse function, Dirac delta function, step function, unit step function. You might see in ramp. Ramp means, see, the name wise it is ramp, it is nothing but a straight line which is starting from origin. See, y is equal to mx is a straight line which is passing through origin. In the same way, ramp is a straight line which is starting from origin, it is not passing through origin. We will see. After that, parabola. Yes, in intermediate parabolas you drawn. If you observe, this is the parabola what you drawn. Yeah, this is also a parabola what you drawn. Yes, what you drawn. So all these things you learned, but what electrical people will complain is, we do not have signals and systems in BTech. That's why we are a little slow. No, you need not to be slow because all these things what I'm going to discuss, you already discussed in your what you call intermediate or BTech. Somewhere definitely all of you might see. Therefore, concentrate very well. Though you are not aware of it, I will be giving you complete clarity. Okay. The first signal I'm going to discuss here is impulse. Yes, the first one is what, ma? Impulse. Impulse signal or impulse function. Impulse signal or impulse function. See, initially our analysis must carry out in which domain? Time domain or frequency domain? Time domain, because human understandable domain is time domain. After completely discussing in time domain, we will convert the given signal into frequency domain for the purpose of calculation. So why calculation is easy, we will discuss later. Yes, it is represented with a function del. Yes, that is called as del. As we are discussing in time domain, yes, del of t. Representation of the signal is what, ma? Del of t. Del is a symbol in bracket t. What is the definition of it? What is the definition of it? This definition is given by the scientist. Yeah, we are not having any command on what you called why here only, why not there only. That is already defined by someone, that is scientist. We have to obey it. Okay, come on. Del of t is equal to, what scientist is saying is, impulse signal value is equal to infinity. Yes, where t is equal to 0. Many of you having a wrong concept with respect to this one. Some people will say del of t equal to 1. No, never del of t equal to 1. Area of the unit impulse is 1. I am stressing once again. Most of you learned this signal in a very wrong manner. Yes, in a very wrong manner. That is, magnitude of impulse signal where at t is equal to 0 is infinity is equal to 0 elsewhere. Elsewhere, t not equal to 0 means what? Anywhere other than t equal to 0. Observe this one carefully. A very beautiful conclusion you're going to get. That is, this signal will exist only at t is equal to 0. This signal will exist only at t is equal to 0. Del of t equal to infinity at t is equal to 0 is equal to 0 at any place other than t is equal to 0. This signal will exist only at t is equal to 0. Let's represent by using a graph. Let's represent by using a graph. Come on, that is t. Yes, this is 0, 0. At t is equal to 0, what is the magnitude, ma? At t is equal to 0, the magnitude of the signal is infinity. Yes, it is not possible to show infinity on board. That's why I'm keeping that arrow. That arrow indicates that that signal is tending towards infinity. Is there any value at other than t is equal to 0? No. Whatever, wherever the point you want to find. At t is equal to 1 you want to find. At t is equal to 1, how much is the magnitude? 0. No value. At t is equal to minus 1 you want to find. What is the magnitude? 0. No signal. Only at t is equal to 0, how much is the magnitude? Infinity. At t is equal to, other than t is equal to 0, how much it is? 0. At t is equal to 0, infinity. Other than t is equal to 0, how much it is? 0. This is the definition of ideal impulse. Ideal impulse. Okay. And here one thing I want to tell you, it is not del of t, it is a del of t. Yes. If a is equal to 1, then we call it as a unit impulse. Yes, I forgot to write previously. A del of t. A del of t. You may be thinking, sir, a del of t, a into infinity is whatever you multiply with infinity, it will be infinity. Yes or not? Yes. Therefore, a del of t is equal to infinity at t is equal to 0 is equal to 0 at other than t is equal to 0. This will exist only at t is equal to 0. Sir, you told mathematically it's okay, but somewhat it is difficult for us to understand practically. Means where it is useful, how it is useful. Does it is possible to get infinite value of signal value within 0 time? Yeah. For how much amount of time this signal is existing? For how much amount of time that signal is existing, boss? Within 0 time. 0 means 0, please. 0 means 0. Not millisecond, microsecond or nanosecond. 0 means 0. Means, is it possible to have infinite amount of magnitude within 0 time? Practically not possible. Yes, practically this signal does not exist. So then what is the use of it? Why we taken it? Just for the purpose of examination? No, please. This one is used at many places in many analysis you will be learning in signals and systems. Okay, but how we are going to use this one? We are not going to use ideal impulse practically. Practical impulse is defined separately. Practical impulse. See, I'll tell you, sir, how this is used. Suppose earthquake occurs. How much time it takes for earthquake? Within microseconds, earthquake will come. How much is the force or how much is the impact of the earthquake? It is very, very high. Within very less time, anything huge happens, then that can be modeled as impulse. Suppose lightning strokes comes. Lightning strokes. What is the light intensity of that lightning stroke? Very, very, very high, right? Within how much time that lightning stroke will disappear? Within very, very less time. Means I'll tell you like this. See, if something happens in a huge amount within very small time, that can be represented with help of impulse practically. So I can say impulse force. Impulse force means large force, you can say. See, there is a lot of difference between large force and impulse force. Large force means the amount of magnitude of the force is high, but impulse force means a large amount of force within very less amount of time. That you have to understand. Large amount of force within less amount of time is called as impulse force. Impulse reaction, huge reaction within less time is called as impulse reaction. So practically ideal impulse does not exist, right? Within zero time nothing will happen, within zero time nothing will happen, but here within zero time, how much is the magnitude? Infinity. At least instead of this one as zero, if that time taking for the signal maybe microseconds or nanoseconds, we can accept, or picoseconds we can accept, but how much it is here? Zero. Exactly, it is zero. Therefore practically ideal impulse does not exist. Okay, fine. So let's see what is the practical impulse, how it is used, all those things. Now there is one more way of representing the impulse. We represented impulse in a graphical way, and we represented it in mathematical way. One more way of representation is what the scientist is saying is area under the impulse is A. Area under the impulse is what? A. How to find the area? How to find the area? Come on, brother, you can give the answer. How to find the area? Area we'll find by using integration. Integration means nothing but finding the area. Please do remember, if you are integrating any function, means you are finding area under that function or signal. Okay. So what he is saying is area. Area means what? Integration of that what? Impulse signal. A, please. This is A. We'll write again. Come on, dear. Here you must understand in this way. Mathematics can be understood in this way. When I am writing this one area, you have to understand. If I am writing integration means area under what? Impulse is equal to how much ma? A is saying area under the impulse signal is equal to A. Sir, you said integration. That integration must have limits, na? Yes. You take from minus infinity to plus infinity. Who bothers? Nobody will bother. Why, sir? Where your signal is existing only at t is equal to 0. Even if you take from minus infinity to plus infinity, or minus 1 to plus 1, or minus 0.1 to plus 0.1, there is no change. There is no much change in it, because signal is existing only at t is equal to 0. Or the same can be written as integral of 0 to 0, yes, a del of t dt is equal to how much ma? A. Now from this what I can understand, A I'll take outside. A is a constant, and there is a constant in the multiplication form that can be taken out of the integration. You know it from mathematics. A integral 0 to 0 del of t dt is equal to how much ma? A. Now what we are in a position to understand, that is integration of 0 to 0 del of t dt is what? 1. Yes. Yeah. If this is 1, then only it will be A. Yes or not? Yes. So here one thing I want to mention. Yeah, you might got a lot of doubts here. I'll clarify all those doubts. What is that? Sir, who given this expression? This expression is given by the scientist. It is not in our hands. We can't prove it. Yes, we can't prove it. This is an expression. Yeah, we can't prove it mathematically, but we can prove it by taking some example. Yes, I will be proving here. Practical impulse I will take. And from the practical impulse, we will proceed towards ideal impulse. Please do have some patience, then you will be understanding everything. Okay? Come on here. Come on, brother. One thing I want to tell you here. Sir, integral of 0 to 0, any signal, how much ma? 0. Except this impulse, means I'm writing here a very important note point, which is useful practically for interviews. Yes, sir, where it is used practically for interviews? In third chapter, we'll see when we are discussing about standard first order system with the impulse input. Impulse response of standard first order system I will discuss in third chapter. At that point of time, I will tell you that is, note is integral 0 to 0 any f of t dt equal to 0, because mathematics integration is saying that the integration limits are same. After integration, if you substitute, what happens? This minus that will be 0, because both are exactly equal. 0. except for any function, for any f of t, I'll write here, for any f of t, yes, for any f of t, yes, except for impulse, except for f of t equal to del of t, f of t equal to del of t. Integral of 0 to 0 del of t dt, how much ma? Equal to 1. Keep this in box, brother. Keep this in box. Very important. Okay? Means except this one, you take any f of t. F of t may be sin t, cos t, tan, whatever you take it. Integration you do from 0 to 0. It will be 0. It will be 0. 1 to 1, 2 to 2, whatever it is the limitation. See, same limits if you are taking upper limit and lower limits are same. Integration will be 0. Except for impulse. But one thing I want to clarify here, that is, practically does it possible to have anything within 0 time? See, I'll tell you one thing. If you switch off a fan, does it stop suddenly? No, it takes some time. Why? Because the fan is rotating till now. That fan is having some kinetic energy in the rotor body. For that energy to become equal to 0, even if you switch off, that energy slowly becomes 0. Why? Because it is already attained some kinetic energy, or you are running very fastly. If I ask you to stop, after completion of my words, will you stop? No. Why? Because your body attains some kinetic energy. That energy to become equal to 0, definitely you need some distance and time. In the same way, practically it is not possible for anything to happen within 0 time. But it is very, very, very less time. To represent that less time, instead of 0 to 0, we will take it from 0 minus to 0 plus. 0 minus to 0 plus. 0 minus to 0 plus. Sir, what is this 0 minus and 0 plus? What is this 0 minus and 0 plus? Let me tell you about this 0 minus and 0 plus. Observe it carefully, please, here. Now, this is the time. Understanding this 0 minus and 0 plus is very, very important with respect to network analysis, transients chapter also. Okay, a lot of you having confusion with respect to time. Let me discuss about time now. Now I am taking a switch here. Let me take switch first instead of this time axis. Let me take switch first. Let us take a switch. Okay, that is a switch, and we are trying to close a switch or open switch. Not a matter. You close it or open it. Yes, we taken a switch. Yes, this is time axis. Okay, come on here. Now we are closing the switch at t is equal to 0. This is t. Yes. Now this is 0. This time is 0. Many people have confusion. Sir, what t is equal to 0? Always t is equal to 0. T is equal to 0. T is equal to 0. Actually, we measure our time in terms of hours, minutes, and seconds. What is this t is equal to 0? I'll tell you one thing. T is equal to 0 is the present time. Now, see why t is equal to 0 is used. T is equal to 0 represents the switch is closed now. Means if you start to solve the problem now, what you have to understand is you have to close the switch, then you start the problem. Means now. T is equal to 0 means now or present. T is equal to 0 means what? Now or present. After t is equal to 0 represent what? This is future. This is what? Future. Before t is equal to 0 represents what? Past. This is past. Now, simply for an example, I will tell you. Actually, again, let's take that axis, time axis again. Let's take that time axis again. Yes, this is t. This is t. Now, let me take 0 here. Let me take 0 here. Now, after 0, what we have? 1, 2. What is this? Minus 1. What is this? Minus 2. Now, you might be thinking, sir, you gone mad. Time never be negative. Why you taken time negative? No, brother. Here, time may be negative. Why? Because present, suppose if it is morning 10 o'clock now, morning 10 o'clock. You are closing switch at morning 10 a.m. You are closing the switch at morning 10 a.m. But I am considering that 10 a.m. as 0. I am considering that 10 a.m. as 0. Yes, I can. Yes, I can. Yes. What I told, t is equal to 0 represents now or present. I am closing switch at 10 a.m. 10 a.m. is taken as 0. Then what will be 11 a.m.? Suppose if I am talking in terms of hours, it will be plus 1. What will be 9 a.m.? 9 a.m. will be minus 1. Minus indicates the time before the operation started. What does it mean by operation? Closing the switch here. Means if you close the switch now, the time before closing the switch is called as past. That past time is negative in mathematical representation. Vice versa. If the time given in mathematical way is negative, what you have to understand is that time represents before closing your switch. Okay, before closing your switch. All these things are very important for me in control systems. If you are very clear with all these things, many problems, just by looking at the problem, we are in a position to understand without putting pen on paper. Okay, trust me, we are going to solve problems in that way, but clarity is very, very important. Okay, yes, sir. 8 a.m. is called as what? 8 a.m. is called as minus 2. For example, I'm saying this thing. Please do not take it as granted. Means concept is granted, but sir, we are taking time in seconds here, but it is hours now. Why you did like this? All those things will not rise here. Just I am giving you the insight of it. Okay, yeah. Now 12 a.m. is called as what? 12 p.m. 12 p.m. is called as what? How much it is, man? Yes or not? Yes. So positive time represents after closing the switch. I'll list out the point here. Yes, note point here. I'll be writing note here. Observe, note. Come on. Yes, you have to observe, understand, remember, and execute. Okay. Positive time means after closing the switch. After closing the switch. Yes, dear. After closing the switch. Yes. Negative time means before closing the switch. Yes, time, positive time and negative time. Now come on here. So this is future. Now you are here. Now you are standing here. This all will be future for you. After 1 hour, 2 hour, 3 hour. See, now the time is 10 a.m. Suppose say 12 p.m. will be future for me. Okay, 8 a.m. will be past for me. It is already done. So this is about positive time and negative time, and this time axis. Now, what we taken previously, 0 plus and 0 minus. Let's understand about the 0 plus and 0 minus. Now, come on, 0. 0 is a very small value. See, 0 minus. See, I'll be taking switch again here. This is t. Switch is closed at t is equal to 0. Now, t is equal to 0 minus. 0 power minus indicates just before closing the switch. T is equal to 0 minus is what? Is just, come on ma, before closing the switch. Just before closing the switch. Sir, before closing the switch, just before closing the switch, what is the difference? Lot of differences there. Underline this just. See, I have a question for you. Now the time is 10 a.m. suppose say. What is the time before 10 a.m.? Please understand the question very carefully. The understanding question itself will give 50% of the answer. What is the time before 10 a.m.? Maybe 9 a.m., 8 a.m., 6 a.m., 7 a.m. or 5 a.m., 4 a.m. or yesterday, day before yesterday, last year, last decade or last year. Let's keep going. Means we don't know. Now today 10 a.m. before time I want. It may be anything. Okay. But what it is just before 10 a.m. Just before 10 a.m. means what? 9 a.m. 59th minute. 59th second, 999, whatever maybe the last possible nearest value to this one that we have to take. Yes, just before means very near. How much near means magnitude wise both are equal. Sir, if magnitude wise both are equal, why we are taking that as a different thing? Yes, we have to take. Why? Because Magnitude wise may be equal. Why? Because we may take a small possible approximation, but operation wise not same. Why? When the switch is closed at t is equal to 0, t is equal to 0 minus means what? Switch is not yet to close, it is about to close. It is very near to close. Means it is very near to close, but not yet closed. Yes, t is equal to 0 means what? 0 minus means what? Just before closing the switch, 0 minus is equal to what? Minus of 0.0000. Your wish. How many zeros you can keep, those many zeros you can keep. Okay. Yes, this is 0 minus. Magnitude wise it is nearly equal to 0, but what 0 minus indicates? Minus time indicates that switch is not yet closed, but this magnitude indicates that it is very nearest to the closing. It means you can't explain that much near it is. Okay, 0 plus means what? 0 plus is equal to, yes ma, plus 0.00. Or first of all we have to write t is equal to 0 plus means just after closing the switch. T is equal to 0 plus. T is equal to 0 plus means just after closing the switch. Just after closing the switch, I can write here like this. Yes, just after closing switch. See, underline this just. Again I am saying, after closing the switch, what is time? Suppose if the switch is closed at t is equal to 0, maybe 1, 2, 3, 4, 5, 6, 7, 8, any seconds. But the just is saying, if switch is closed at t is equal to 0, 0.000000000001 is called as just after closing the switch. So I am writing here 0 plus is equal to 0.000000. How many number of zeros you want to keep? Those many number of zeros you can keep. 0 zeros 1. So this is the meaning of t is equal to 0 plus. So I am writing here magnitude of 0 minus 0 plus is equal to 0 magnitude wise, but operation wise 0 minus and 0 plus and 0 all three are not same. 0 minus is just before closing the switch, switch is not yet closed. 0 plus means just after the closing the switch. 0 means at the time of closing the switch. This is the difference between 0 minus and 0 plus and 0. One more simple example I want to give those who did not understood about 0 minus and 0 plus. Yeah, you told me that you came to the class at exactly 9 o'clock. At exactly 9 o'clock. Means this is the class entrance. Class entrance is this. Okay, this total is class. This total is class. Now, exactly at 9 o'clock, you are here. 9 o'clock you are in the class. Exactly. Just before 9 where you are? Just before 9. Means 8 o'clock, 59th minute, 59th second after that, whatever may be the fraction, till that fraction where you are? At the very entrance of the class. Just after 9 o'clock. Means 9 o'clock after that in one not even 1 second, in 1 second, in 1 second 10 to the power 12th part where you are? In class. But you are not completely entering into the class, very near to the after entrance of the class. Means what I want to tell you here exactly here is, just before entering the class you are out of the class but very near to the entrance. Means you and that entrance both are touching. Just after entering the class, you are not completely into the class, you are nearly the entrance, but this side with what you call the attachment. Means you are still in touch with the entrance, but this side. See, if this is the entrance, yes, I am taking here. If this is the entrance, this entrance width is 0. If that entrance width is very small, or it is not possible to take 0. Now, just before 9 a.m., you are touching this side. Yes, just after 9 o'clock, you are this side. Okay, in that way you have to understand about 0 minus and 0 plus. Now 0 minus to 0 plus integration of del of dt is equal to 1. Integration of del of dt is equal to 1. So 0 minus, 0 plus and 0, all three are operation wise not same but magnitude wise are same. What we learned here is integral of 0 minus to 0 plus del of t dt equal to 1. What that is? That is impulse or unit impulse? Unit impulse. If it is a here, yes, this will be what? That will be a. Now that is impulse of area a. This is what? Impulse of area. Impulse of area a. Area a. Now come on here. Now all of you observe here. If a is equal to 1, if a is equal to 1, then that signal is called as, come on ma, is called as unit impulse. Unit impulse. What you have to understand is impulse is represented with a graph whose magnitude is tending towards infinity and it is equal to 0. That is one way. Another way is definition del of t is equal, a del of t is equal to infinity and t is equal to 0, equal to 0 at any point other than t is equal to 0. Another way is with area, integration of any signal. See, note, those who are not good at mathematics in their intermediate, yes, they must understand this point. Integration of f of t dt, integration of f of t dt will give the area, under f of t, will give the area under f of t. Yes or not? Yes. So integration of del of t will give area under impulse. Integration of del of t will give area under impulse. Now come on here. Now example. Now if the below signal represents impulse, yeah, please do understand this example, very important example. Let me see how many of you are going to give the correct answer. If the signal shown below is an unit impulse, then x is equal to dash. Let me draw the signal, please. This is t. Now this is t. This is f of t. If the f of t is an impulse, what is the x is saying? What is the x is saying? Let me draw it again. Yes, read the question carefully, please. Read the question carefully. All of you. I want answer from all of you. This is very simple. X is equal to dash is asking. Come on. Read the question once again. If the signal shown below is an unit impulse, x is equal to dash. Now the first question that rises in student's mind is, sir, you drawn an impulse whose magnitude is tending towards infinity and width is 0, but you drawn a rectangular here and you are saying that this is an impulse and all these things. Why we have to bother? The examiner only said that the given is impulse. Which impulse? Unit impulse. Understand this. Unit impulse. Unit impulse means what, ma? Solution I'm doing here. I think many of you got the answer by this time. Unit impulse means what? Area under, yes, impulse. Area under impulse is equal to how much, ma? 1. Area under impulse is equal to how much? 1. What is this value? 2. What is this value? -2. What is this width? 4. For this area, under this area to be equal to 1, what is the formula? X into 4. Yes, x into 4 must be equal to 1. Length into breadth. Yes, length. So this one is how much? 4. -2 plus 2. Distance is 4. Height is how much? X. This width is 4. Height is x. Width into height is equal to, width into height equal to 1. Therefore, x is equal to how much, ma? 1 by 4. That's it. So the first confusion the student will get is, sir, the given signal is looking like a rectangle or a rectangle, but you are saying it as impulse. How it is? We are least bothered about it. He only said the given is a unit impulse. Unit impulse means the only thing that you have to remember is area under the curve must be equal to, or area under the pulse must be equal to 1. Area under the impulse must be equal to 1. What is area? This into this, width into height. 4 into x is equal to 1 by 4. Now I will tell you how to get ideal impulse from this practical impulse. This is the practical impulse. How to get the ideal impulse? Come on. Obtaining ideal impulse. Observe carefully. Yes, all of you must observe carefully, ma. So impulse is very important. That's why we are spending this much amount of time on this. Okay. Not only here, in other subjects also this is useful, like signals and systems, or to some extent say in other subjects like signals and systems and control systems. Not in other subjects you won't encounter. Maybe in your communication systems, yes, in communication system we see people. For triple people only in control systems and S&S. In other subjects, yes, when we are not having any use. Okay, come on here. This is -2, this is +2. Yes. By keeping area constant, what is this, ma? This is 1 by 4. By keeping area constant, if t is reduced, what happens? Height will increase. Yes, I am writing here, if by keeping area constant, if t decreases, then x increases. Let's call this height as x. Yeah, we are calling height as x, where I represent here, where x is equal to height. Now come on here. I am reducing this one from -1 to +1. Then definitely this will become. Let's see. What is the area? Area equal to 1. Yeah, we know it. Previous example only was 1 by 4 into 4. How much it is? 1. Now this is -1. This is -1. This is +1. Now definitely this height, that height will definitely increase. Sorry. Let me draw it again. Not an issue. Come on here. Yes. Come on. Now we are increasing the height. Why? We want to keep the area constant. Area should not decrease. If this width is decreasing, height will definitely increase. Then how much it will be? 1 by 2. Now I'll say, yeah, if that t is tending towards 0, I'll write here. If t is tending towards 0, that implies x will tend towards infinity. We approach it to ideal impulse or not? Yes, very much. If this is decreasing towards 0, means further I'll draw like this. Further, if you decrease, height will increase like this. This -1 by 2. This is 1 by 2. This will be definitely 1. That will be 1. You draw perfectly. Somewhat it is tilty here, but not an issue. Observe here. Means if this width is decreasing, height will increase. If this width is becoming 0, height will become infinity. So in this way, from a practical impulse, yes, unit impulse, what we taken previously is rectangular form. Yes, it is practically possible. But if you are decreasing this width, this height will increase. Yes or not? Yes. So this is the impulse signal definition and its representation, how to get practical impulse and all these things in time domain. Let's convert this into frequency domain. Now one point I want here, yeah, we'll discuss after converting into frequency domain. Yeah. Now f of t is a signal in time domain. How to get f of s Laplace transform? You will get a f of s. Now del of t, I want here a del of t, Laplace transform f of s is equal to how much? Let's calculate. I told you very easy. What is the procedure? F of s is equal to integral minus infinity to plus infinity, f of t, this is e power minus st, we are taking the kernel dt, yes, integral minus infinity to plus infinity. What is f of t? A del of t, boss. A del of t into, sorry, a del of t e power minus st dt, a del of t e power minus st dt. But while we are doing integration, definitely we have to check the common limits. These two are in multiplication form, yes or not? Those two are in multiplication form. Now, where this signal del of t will exist, I am writing here. Del of t will exist. Where ma? Only at t is equal to 0. Del of t will exist only at t is equal to 0. Means, tell me, if two functions are in multiplication form, multiplication means what happens? Common area only will be multiplied. Yes, common area only will be multiplied. I'll tell you with an example. So some people are having some confusion with respect to the words what I'm giving. So this is minus 2 to plus 2 into, suppose if I'm giving minus 1 to plus 1. This multiplication will, the result we will get obtained from where to where, ma? Minus 1 to plus 1 only. Because minus 2 to minus 1, this is 0. Here there is some value, but 0 into some value is what? 0. Means in multiplication, only common area will get multiplied. Only common area will get multiplied. Now here, these two are in multiplication form. Del of t into e power minus st, both are in multiplication form. Now tell me, del of t into e power minus st can be written as del of t into e power minus s into 0. Why, sir? Del of t will exist only at t is equal to 0. Only at t is equal to 0. Therefore, I have to take e power minus st also only at t is equal to 0. Why? Because e power minus st will exist anywhere in S plane. This will exist anywhere. That's not in S plane, in T plane. On T axis, at anywhere it will exist. If t is equal to 0, 1, 2, 3, whatever you want, you can take. This will exist. But this exists only at t is equal to 0. Therefore, these two I have to take only at t is equal to 0. In the place of t, I substitute 0. Therefore, how much I got is equal to del of t. Therefore, represent this one with del of t. This product will become what? Del of t. And one more thing, del of t will exist only at t is equal to 0. Come on, this expression will become integral of 0 minus to 0 plus. So why we are not taking 0 to 0? Any practical signal, definitely small width, at least small width. That small may be tending towards 0. But we should not take 0 on 0. So I want to tell that this is just before closing switch, that is just after closing switch, that the distance has to be maintained. And one more thing, the del of t is a signal only at exists t is equal to 0. That is equally distributed towards t, this side and that side. See, what I want to tell you is, this is 0. Suppose if that is there, this side and that side, I can tell you like this. This side small, that side small. Yes, small. That's why 0 minus and 0 plus. Come on here. Yeah. 0 minus 2, 0 plus. 0 minus 2, 0 plus. A is A. Del of t is del of t. E power minus st, how much it is? 1. Because t is equal to 0. dt. Now, A I taken outside. Integral of 0 minus to 0 plus del of t dt is equal to how much? This particular value is how much? This particular value is 1. Yes or not? Very much yes. That particular value is 1. A into 1 is how much? A. Sir, how do we know that the integral of 0 minus to 0 plus del of t dt is equal to 1? From the definition given by the scientist, area under unit impulse is equal to how much? 1. Let's list out those points here, what we learn. Let's list out, come on here, integral of 0 minus to 0 plus del of t dt equal to 1. Yes, keep it in box. Yes, all of you, at any point of time we may use this one. Okay, please do remember that one. Now, what we got? F of s. Yes, come on, let's go back. We are finding the Laplace domain, what you call the function of f of t. F of s is equal to how much we got? Yeah. Come on here. That is equal to, yeah, we started here. F of s minus infinity plus infinity f of t e power minus st dt. Integral minus infinity plus infinity a into del of t e power minus st dt. Yes, we completed it. We got a. Now, there is a confusion for students. Now, f of Laplace transform of A del of t. A del of t. How much we got? Yes. Laplace transform of A del of t. How much we got? A. People might misunderstood. I did not done the integration here. Integration is the second part, mathematical part. But what is my aim? My aim is finding f of s. My aim is finding f of s. Let me write here. Otherwise you will forget. Otherwise you will forget what we are doing. Yes, most of you will forget what we are doing. You will be concentrating only on this mathematical operations, but you forget the main aim of our finding. Laplace transform of A del of t. How much we got? Laplace transform of A del of t. I got it as A. Very important. Now I have a question. This A is in which domain? Some people, without thinking, they will give the answer as time domain. No. If you find Laplace transform for a signal which is in time domain, then the obtaining answer is in which domain, ma? S domain. S domain. Though S is not shown in that, but because S is not there, Laplace transform of impulse function is a constant. That's why S is not available here. Now come on here. Before that, an example. Let me ask you. F of t equal to 1. This 1 is in which domain? Time domain. F of S is equal to 1. That is in which domain? Frequency domain. But some people will see, sir, this is 1, this is also 1. Why this is in time domain? Why this is in frequency domain? Look at this. This is the reference for us. This is in time. This one is in time domain. This one is in frequency domain. In the same way, my signal is in time domain. I applied what? Laplace transform. I got some result. That result must be in S domain. Now, the note point here is, the note point of the formula what we have to remember is Laplace transform of del of t is how much, ma? Equal to 1, boss. 1 Laplace transform of unit impulse is 1. Why? A equal to 1 here. If you put A equal to 1, I got this one. Laplace transform of A del of t, or first write this one, next that one we will write. First formula. We derive it, after that we will remember. If you forget also, you can derive with the procedure what I given. Laplace transform of A del of t is equal to A. Yes, Laplace transform of del of t is equal to how much, ma? 1. Now I will be asking you a question. Try to give the answer. Yes. What is inverse Laplace transform of 2? Yes. 30 seconds will be the time given to you. Inverse Laplace transform of 2. Sir, you didn't explain anything about inverse Laplace. How are you asking about inverse Laplace? You can answer with what we discussed till now. Answer is 2 into del of t. Sir, how, sir? Let me do. Laplace transform of A del of t is equal to what, ma? A. We proved it. We got by using the calculation from my integral of 0 minus to 0 plus A into del of e power minus st dt. We calculated. We got A. Then apply inverse Laplace on both sides. Apply inverse Laplace on both sides. Yes, inverse Laplace transform on both sides. Yes. Now inverse Laplace of A del of t, yes, is equal to inverse Laplace of A. Now inverse Laplace of A is equal to Laplace and inverse Laplace both gone. How much we got, ma? A times of del of t. A is some constant, whatever may be the value. A may be 0.1, 0.3 or 0.4 or 2 or 3, whatever may be the value. So Laplace transform of what I asked here. I asked here Laplace, inverse Laplace transform of 2. Inverse Laplace transform of 2. A is 2. 2 into 1 it can be written as 1 is what? 2 into del of t. Inverse Laplace of 1 is what? Del of t. So in this way we can easily understand. Now one more example, if I ask what is the inverse Laplace transform of 10? That is 10 del of t. 10 del of t. Now if I ask a question, yeah, the next question I am going to ask. Many of you will give wrong answer. Try to give the correct answer for me. Laplace transform of 1 is dash. Laplace transform of 1 is dash. Yes, very good question. 99% of the people will give the wrong answer. People will give it as 1 del of t. 1 del of t. Absolutely wrong. Why, sir? I asked Laplace or inverse Laplace? Laplace transform. By keeping the previous one in mind, inverse Laplace of 10 is 10 del of t. Inverse Laplace I am applying means what? This 10 is in which domain? S domain. Answer should be in time domain. Here what we are doing? We are applying Laplace transform to this one. Therefore, what is this one? f of t equal to 1. F of t equal to 1. Then answer must be in which domain? S domain. Or some people will give it as a 1 into del of s. 1 into del of s. Bullshit. There is no such function as del of s. We didn't define. I want Laplace transform of 1. Find in a normal processor. These are the two possible mistakes committed by the students. That's why I am giving solution. First of all, let's draw f of t equal to 1. Let's draw f of t equal to 1. F of t equal to 1. Irrespective of time, it is always 1. No? Yes. I did not given f of t equal to 1 for t greater than 0 or t less than 0 or t equal. In that way, I did not given f of t equal to 1 for all t greater than 0. Therefore, if I draw the graph of it, this is t, this is 0, this is 0. Yes, this is a function. This is f of t. This is f of t. This is the graph. F of t equal to 1. Means irrespective of time, from minus infinity to plus infinity, it is always 1. Means function is existing everywhere. Function is existing everywhere from minus infinity to plus infinity. Come on here. F of s is equal to, come on ma, integral minus infinity to plus infinity. Integral minus infinity to plus infinity. How to find f of t? What is f of t? F of t, let's take it as f of t. E power minus st dt. E power minus st dt. Integral of minus infinity to plus infinity. F of t is how much? 1. F of t is how much? 1. E power minus st dt. Now 1 is anyhow, 1 into anything will be the same thing. E power minus st integration e power minus st by minus s from minus infinity to plus infinity. Now come on here, do the calculation carefully. I'm doing the calculation. Observe. That is equal to f of s is equal to e power minus st by minus s. Yeah, let's substitute the limits, please. Let's substitute the limits first. S minus s you take common, minus 1 by s e power minus s into t equal to how much more? Lower limit minus infinity minus e power minus s into infinity. Come on, f of s is equal to minus 1 by s, throw that inside, e power minus s into infinity minus e power s into infinity, minus gone. What is e power minus s infinity? 1 by e power infinity. This is e power infinity. This is anyhow 0, but this is what? Infinity. Yes, that is what? Infinity. Means the answer is converging or diverging? Diverging. Yeah, see, it should, f of s is equal to how much we got? Minus infinity. F of s is equal to minus infinity is not a function. It's not a finite value. Therefore, I can say Laplace transform of 1 does not exist. Many people will give answer like this. What is that? Laplace transform of 1 is equal to directly 1 by s. Directly 1 by s they'll give. If you ask any people, they'll give it as 1 by s. Absolutely wrong. Absolutely wrong. You might learn in your BTech classes Laplace transform of 1 as 1 by s. No. Laplace transform of 1, yes, what ma? Does not exist. So then in BTech we learned it as 1 by s. What's the wrong we committed there? We have two types of Laplace transforms. That is, yes, a very important note point. A lot of students will get confused in examination. Observe here. Note that point is we have two types of Laplace transforms. One is unilateral. What is that, ma? Unilateral Laplace transform. Unilateral Laplace transform, that is f of s is equal to integral 0 to infinity f of t e power minus st dt. That is called as what, ma? Unilateral Laplace transform. Second one is, yes, bilateral. What, ma? Bilateral Laplace transform, that is f of s is equal to integral of minus infinity to infinity f of t. This is looking like del of t, ma? This is not del of t, that is f of t. Let me write it again. F of t e power minus st dt. Now come on here, sir, in examination just he didn't ask about anything unilateral or bilateral. He just asked Laplace transform what to do. Yeah, the question is again the same question I'm taking as same previous question I'm taking. First one, find Laplace transform of f of t equal to 1. Now the point here is we wrote 2 points, unilateral Laplace transform and bilateral Laplace transform. Sir, what we have to find, unilateral or bilateral? If you find Unilateral, you have to take limits from 0 to infinity. If you take limits from 0 to infinity, you will get the answer as 1 by s. I will prove it. If you take from minus infinity to plus infinity, answer is minus infinity, which does not exist. So then what we have to find? We do not have any clarity. Now, a note point I am giving here. Lot of note points I will be giving in this chapter. Note A. Laplace transform means by default, yes, bilateral. What ma? Bilateral Laplace transform means if the examiner didn't mention anything about the transform, means either it is unilateral or bilateral. By default, we have to do bilateral. So then what about unilateral? If he require in this way, like if he require unilateral Laplace transform, he will mention. You got the point, ma? If it is required for him to mention, if he require unilateral Laplace transform, he will mention. Okay. What is the answer? Find the Laplace transform of f of t equal to 1. What is the answer we got? Answer we got it as does not exist. Just now we did. Does not exist. Now see the question. Now see the question. Yes. Second one. Find unilateral Laplace transform of f of t equal to 1. Now he mentioned that very clearly he want unilateral Laplace transform. Now do the solution here, please. Solution. See, f of s is equal to integral where to where? 0 to infinity. Why? Unilateral means where to where? 0 to infinity. F of t is 1 into e power minus st dt. That is what? E power minus st by minus s from 0 to infinity. Minus 1 by s take common. E power minus s into s. What is this, ma? 0. Infinity, please. Infinity. Upper limit first, then lower limit, right? E power minus s into 0. So how much you got? E power minus s into infinity is 0, because 1 by e power infinity will be 0. E power minus s into 0 is how much? 1 minus 1, but how much it is? 1 by s. I think previous we wrote we substituted limits wrongly. You can please check. First lower limit we have to substitute. First upper limit we have to substitute here. Yes, we substituted the same. Yes. No, we did wrongly here. Yeah, we did wrongly here. No issues. You can correct it. Okay. What I did is first I have to substitute upper limit, then lower limit. I substituted first lower limit. You can check it, but whatever it is, plus infinity or minus infinity, answer does not exist. Answer should be a finite value or a function, but it should not be in terms of infinites. Okay. Come on here. What is the answer we got? 1 by s. Now you can get the clarity. Laplace transform of 1 is equal to 1 by s. If you calculate unilateral Laplace transform of 1 does not exist for bilateral Laplace transform or Laplace transform. See, Laplace transform, if not mentioned bilateral, by default it is bilateral. Okay, so this is the clarity for unilateral Laplace transform. So in examination, if the examiner asks one question given in GATE 2012 for 1 mark, what is the unilateral Laplace transform of some function? Unilateral Laplace transform means where to where we have to calculate 0 to infinity. If I calculate from 0 to infinity for 1, definitely you are going to get 1 by s. If Laplace transform is asked, Laplace transform means what? Bilateral Laplace transform. Where to where the limits we have to take from minus infinity to plus infinity. Answer will be does not exist. In the previously I taken what you called limits in reverse way. Please correct it. No issues. See, or if you have doubt that also I'll clarify here what is the small error I committed here. Let me erase it. Here. We will do it again. Yes. Let me erase it. Just substituting limit. In overlook I substituted like that. Yes. What we got? F of s is equal to minus 1 by s. What is the upper limit? E power minus s into infinity. Yes. Minus e power minus s into minus infinity. That's it. Minus s into infinity, minus s minus infinity. So if I substitute, if I send this minus inside, how much I'm going to get? E power infinity minus e power minus infinity by s. How much it is? Infinity minus 0 by s, which is equal to infinity. Therefore, does not exist. Does not exist. Some people will get it duped. Sir, why can't we take a Laplace transform of one, bilateral Laplace transform of 1 as infinity? No, please. Infinity is not a function or a finite value to define. Means, see, I'll tell you one thing. Why we should not take Laplace transform of 1 is infinity. Laplace transform of 2 also will become infinity. See, for one function, one particular Laplace transform only should exist. Means, if Laplace transform of f of t is f of s, Laplace transform of g of t is g of s if f of t is not equal to g of t. So here Laplace transform of 1 also infinity, 2 also infinity, therefore wrong. Means infinity should not be the answer, does not exist. So sometimes in interview this question may be asked, what is Laplace transform of 1? Then some people without having good knowledge on Laplace transform, they will answer it as 1 by s. Wrong. It should be does not exist. If you say the answer why it does not exist, the interviewer will ask the next question, why it does not exist. Then you can prove like this, sir. Laplace transform f of t means f of s, g of t means g of s. If f of t is not equal to g of t, then f of s should not be equal to g of s. If I take either 1 or 2, whatever it is, Laplace transform is becoming infinity. Infinity is not a function or a finite value. Therefore, Laplace transform of 1 or 2 or 3, any constant which is existing from minus infinity to plus infinity does not exist. So this is the answer what you have to give. So we are done with what you call impulse signal. The next signal what we have to discuss here is unit step, or first we will discuss step function. After that we will go for unit step function. Here in this discussion we are done with impulse as well as unit impulse. Impulse as well as unit impulse, converting from time domain to frequency domain and frequency domain to time domain. And its application, whenever application comes at that point of time, we will apply and we will remember there. If I list out all the applications here, you will forget. That's why taking the list of applications is not good here. We will, whenever the time comes at that point of time, we will apply and we will remember. Okay, so please do remember these things. We will go for the unit, not unit, step function. After step function or step signal. After step signal, we will be discussing ramp. After that, parabolic. After sinusoidal, exponential, and some operations like time shifting, frequency shifting, okay, convolution. These things also we will see, and initial value theorem, final value theorem. With this we will be done with our by finding partial fractions, also very important for us. Partial fractions just like that we will write, okay, with the direct inspection method, okay, without using pen paper we are going to write partial fractions. With this we are done with the signals and systems part that is required for the what you call after completion of that we are done with the signals and systems part required for the control system analysis.